Good morning, professors and judges. I'm Law Key from Ching Middle School, and today I'm honored to be here to present you my investigation on the Johnson-Little-Russell question on square posets. The Johnson-Little-Russell question was first proposed by Johnson, Little, and Russell in 2013, and this question remains open. In 2014, Kittipassorn gave partial results and a conjecture regarding the question, which was stated in an unpublished manuscript. But why could I see his manuscript? This is because I joined the Research Science Institute, a summer program for high school students dedicated to scientific research. And this is also where I first encountered the problem. To introduce the question, let's start with a classical question. Given a n by n grid, we want to find the number of paths going from A to B that only go upwards. The total number of paths can be calculated using the following method. The number on each level is the sum of the numbers on the previous levels that it connects to. Now let's consider a variant problem. Instead of all the points in the grid, the path can only pass through the k-selected points. In the example, the red path is invalid as it doesn't pass a point that is not selected. And we can calculate the number of paths by using the similar calculation. In this case, it's 18. Using this notation, and so we denote the number by mt, where t is the configuration of k selected points. Using these notations, we proceed to state the main question in the paper. Considering the following two configurations, we see that mt1 is equal to 3 and mt2 is equal to 10 while they have the same number of selected points. So we wonder, how can we arrange the points on the grid so that the total number of paths is maximized? This is actually the Johnson-Little-Russell question. Given integer k, we want to find a configuration t star with k points such that mt star is maximized. Kittipassorn worked on a constrained question. Instead of arranging points on the grid, points can only be arranged within the same level. For instance, in this 555 grid, it's divided into 9 levels, and the number Li denotes the number of points that can be placed on the ith level. And this shows a possible configuration with the specified Li. The constrained question states as follows. Given the number of points on each level, how can we find a configuration T star such that mt star is maximized? He solved his own question by considering the following configuration, which we will call it Kittipassorn's configuration. For each level, all the points are condensed in the middle, and if we have to break the left-right symmetry, all the extra points are put on the right. And the Kittipassorn's configuration is denoted by T star R1, R2 to R2 n minus 1. And the example on the right shows the Kittipassorn's configuration for the given Li. Kittipassorn proved that if the number of points on each level is fixed, his configuration gives the maximum number of paths. Clearly, Kittipassorn's lemma can be used to tackle the Johnson-Little-Russell question. If we can distribute the k points on the 2n-1 levels suitably, the corresponding Kittipassorn's configuration gives the required maximum number of paths. So, for example, when k is equal to 13, the figure shows an example of the distribution of Ri, and we only have to calculate the number of paths in the Kittipassorn's configuration on the right. So from now on, we will only consider the Kittipassorn's configuration. My work of the Johnson-Little-Russell question then begins. Firstly, consider the case when k lies within this range. We have the following proposition that the maximum number of paths can be calculated by this formula. And to prove this, the key step is the following technical lemma. Given k as the sum of Li, the product of them is bounded above by this term. And notice that the bound is sharp, and we can always find an equality case which is given by this. So applying the previous lemma, we can see that as k is between 2n-1 and 3n-2, the product of Li is bounded by this, which is exactly the value in the proposition. And we take the Li such that the equality case holds, and notice that as k lies within this range, the maximum number of paths is equal to the product of Li, and this completes the proof. So in this proposition, we see that when given the total number of points k, we can directly find the maximum nt and the optimal configuration, which is a Kittipassorn's configuration. However, the range of k is too restrictive. So in the next step, we shall investigate on a more general k, and this requires more observation. Consider the red point V, and notice that it's not connected to any of the paths, so it's wasted. Hence, removing any of the wasted point will not affect the number of paths. So now the question is, how can we improve the configuration? For example, if we move the point from V to U, now it's not wasted anymore as it connects to some path. So Here we divide the question into two parts, namely how to detect the wasted point and how to move it. First, when a point is wasted, when will a point be wasted? We see that the red point V on both of the figures are wasted. On the left, it's wasted because it's not connected to any of the points on the next level, and on the right, it's not connected to the previous level. Therefore, if the difference of points between two levels is greater than 1, then there exists a wasted point. So we now want to relate this idea with the Lipschitz condition. We call that a function is said to be one Lipschitz if the difference between fx plus 1 and fx is always less or equal to 1. And notice that this function is defined in the domain of the first two n-1 integers. Therefore, such a Lipschitz function can formulate a configuration that has no wasted point. And the application of this notation will be provided later in the presentation. We now want to show that we can always improve the configuration whenever there is a wasted point. And to do that, we want to add a useful point. We prove that if the grid is not full, we can always add a point such that the total number of paths increases. Therefore, a useful point always exists. To construct the useful point, we consider a new definition, area. For a path M, we consider the area as the number of unit grids on the left of M without loss of generality. And in this case, the area of M is 11. And for any path, there always exists a turning point where the path either turns from left or from right to left. And we only consider it when the opposite point of it is empty. In the figure on the left-hand side, the two orange points are the turning points. And here we can present the idea to move the wasted point. First, find the wasted point V, then we can remove it. And then we find the path M star with the greatest area. Then we need to find the turning point of it, the orange point. And then we can add a point that is opposite to the turning point. And now the configuration is improved with more possible paths. Now we know how to detect the wasted point and show that we can always improve the configuration when there is a wasted point. Putting those ideas, we can help to find the optimal configuration. To relate this idea of the one Lipschitzness, we define a function f that stores the number of points on the live level and denote t star f as the following. Then we can give the theorem that all the optimal configurations are given by a one Lipschitz function. Therefore, we reduce the number of possible cases to consider in search of the optimal configuration. As a short summary, the Johnson-Little-Russell question originally requires to choose k points in the n by n grid, and now by Kittipassorn's lemma, we only need to partition the n into two n-1 levels. We show that when k is within this range, we can calculate the maximum number of paths by this formula. And we also show that the maximum configuration is given by a one Lipschitz function. So we further reduce the number of cases we have to consider. Now, let us move to some possible future work. Kittipassorn suggests that the number of putting points should be from the middle to size and from bottom to up. So, for example, if k is equal to 9, then we should put the points from 1 to 3 until 9. And this is conjectured to be the optimal configuration. And notice that for small values of k, Kittipassorn's conjecture suggests that each level has at most 2 points. So here we can define U to be the set of configuration T with at most 2 points on each level. And we conjectured a optimal configuration of all T is in the set of U. And this motivates us to calculate the right-hand side. In fact, it can be calculated by the following proposition. It is equal to a product of power of 2 and a Fibonacci number. And to illustrate this idea, consider an optimal configuration when n is equal to 5 and k is equal to 15. So we can see that the maximum of path is 26, and when one point connects, so in the figure you can see that when one point connects to 2 points in the next level, the number doubles, and when 2 points connects to 2 points, the number of paths sums up like a Fibonacci number. So it's not surprising that we get the value in the proposition. As for conclusion, in our paper, we solved the case when k lies within this range, and we also did some investigation on general k, including detecting the wasted point, moving the wasted point, and combining those ideas, how to reduce the possible configurations. And at last, we provided some future work, including the Kittipassorn's conjecture, and we also provided a conjectural solution when k lies within this range. This is the end of our presentation. Thank you.